Hello, welcome to the Midnight Particle. Tonight, we're shrinking reality down until it gets weird. Here, particles vanish for no reason, teleport across space, and somehow know when you're watching them, like nosy neighbors but with PhDs. And the best part? Even the scientists who discovered this stuff don't fully understand it. So, ready to watch the universe break its own rules? Imagine you wake up tomorrow and realize that everything you've ever touched, tasted, or trusted is just a special effect. Not a glitch in the matrix. Something worse, an illusion created by the limits of your senses. Right now, your eyes are feeding you a beautiful lie. They show you smooth, solid objects. Your phone, your desk, your coffee mug. But if you could shrink down, way past what even a microscope can see, you'd find that solid is mostly nothing. Not poetic nothing, actual empty space. A hydrogen atom, one proton and one electron, is 99 point, a whole bunch of nines, 6% empty. If that proton were the size of a blueberry, the electron would be like a dust mote circling a football stadium, and in between, just vacuum. Your skin tells you surfaces are still and steady, but at the atomic level, they're buzzing like a nightclub dance floor. Every atom is vibrating, colliding, and swapping invisible particles at breakneck speeds. If your chair were truly still at the atomic level, it would mean it's frozen to absolute zero, and you'd have bigger problems than understanding quantum mechanics. Even color, that lovely red of a strawberry or the deep blue of the sky, isn't out there. It's just your brain's interpretation of certain wavelengths of light. A bee with ultraviolet vision sees patterns on flowers that to us are invisible graffiti. Reality literally looks different to different creatures. That means what you call real is already just your version of it. Here's the unsettling truth. The reality you live in is a simplified, low-resolution interface, like the icons on your phone. You don't see the actual processes, just the user-friendly shortcuts. Quantum physics is the backstage pass that shows you what's really happening. And spoiler, the backstage is chaos, magic, and nonsense, all rolled into one. Because once we open the curtain and peek into the quantum world, we'll find that the laws we thought were universal, they work only in the polite large-scale world we live in. Down in the subatomic basement, particles teleport, vanish, and act like they have multiple personalities. And just when you think you can handle that, we'll run into an experiment that forces us to ask whether reality even exists when you're not looking. That's where our journey really starts. The birth of quantum theory, Planck's reluctant revolution. If you were alive in the late 1800s, physics looked done. We had Newton's laws, Maxwell's equations, and a universe that ran like a perfectly wound clock. A few scientists even claimed there was nothing left to discover, just fill in the decimals. That statement aged about as well as milk in the sun. The trouble started with something that sounds boring but ended up breaking physics. Black-body radiation. Picture a tiny oven, a hollow metal box that traps light inside. Scientists used it to study how hot objects glow, from red to orange to white. According to classical physics, the hotter it got, the more light it should emit at shorter wavelengths, with no limit. That meant, mathematically, it should produce infinite energy at ultraviolet wavelengths. This nonsense result became known as the ultraviolet catastrophe, which sounds like a bad superhero movie, but it was a real crisis. Enter Max Planck, a German physicist who just wanted the math to work. In 1900, he made what he thought was a purely formal trick. Instead of letting energy be continuous, like water flowing smoothly, he said it could only come in tiny fixed packets, which he called quanta. Like coins instead of a bank transfer. You can't have half a coin, and light couldn't have arbitrary amounts of energy. Planck had no idea this little fudge would ignite the biggest revolution in physics since Newton. He basically stumbled onto the idea that energy is quantized. Reality, at its core, comes in Lego bricks, not Play-Doh. At the time, Planck treated it like a math hack, not a deep truth. But just a few years later, Albert Einstein took Planck's idea seriously and used it to explain the photoelectric effect, showing that light itself was made of particles we now call photons. That 1-2 punch was the birth certificate of quantum theory. Of course, back then, nobody knew they were opening Pandora's box. Planck thought it was a temporary fix. Einstein thought quantum physics was fascinating, but incomplete. Neither of them knew it would lead to particles tunneling through walls, cats in paradoxical states, or computers that could crack every password on Earth. And just when scientists were getting comfortable with the idea of packets of energy, reality decided to reveal something even weirder, that light wasn't just particles at all, but also waves. And that's where things really start to break. Einstein Joins the Weirdness, Photoelectric effect, and the light quanta. If there's one thing quantum physics loves, it's making you pick between two options and then telling you both are correct. And the first time it pulled this trick, the victim was light itself. By the early 1900s, scientists had just made peace with Einstein's claim that light came in little particle-like bundles called photons. It was weird, sure, but manageable. Then someone remembered an awkward fact. Light had already been caught behaving like a wave for centuries. Go back to the 1600s. Isaac Newton, never short on confidence, was convinced light was made of particles he called, quote, corpuscles. Meanwhile, Christian Huygens, a Dutch scientist, argued light was a wave, more like ripples in water. They debated it, and for a while, Newton's celebrity won the argument. But in the early 1800s, Thomas Young came along with his double-slit experiment. Not the infamous quantum one yet, but a purely classical version. He shone light through two tiny slits and saw an interference pattern, bright and dark stripes, exactly what you'd expect from waves overlapping. It was a slam dunk for the wave theory of light. The particle idea was left gathering dust. Fast forward 100 years. Planck and Einstein revived the particle idea to explain black-body radiation and the photoelectric effect. And suddenly physics had a problem. Light could be measured as particles or as waves depending on the experiment. It was like catching your friend in two disguises, both of which are undeniably them. Here's the modern picture. In some experiments, light acts like a wave, spreading out, interfering, creating patterns. In others, it acts like a particle, delivering energy in discrete chunks, bouncing off surfaces like tiny billiard balls. The maddening part? Light isn't switching between these modes. It's somehow both, all the time. The best analogy? Think of light as a celebrity who behaves completely differently depending on the paparazzi's camera settings. Zoom out and you get their glamorous, wave-like public persona. Zoom in and you catch the grainy, particle-like details. It's the same being, just revealed differently. But scientists weren't satisfied with analogies. They wanted math. And the math came in the form of quantum theory's wave function, a mathematical object that describes all the possible states of a particle, including where it might be, how fast it's moving, and how likely it is to show up in a given spot. For light, that wave function neatly explained why photons could interfere like waves and still hit detectors one by one like particles. Still, the idea felt like heresy. Einstein himself called it a kind of ghost field. Bohr, his friendly rival, basically said, "Stop asking what light is. Just ask what it will do when you measure it." It was less of a solution and more of a surrender, an admission that our classical intuition simply doesn't apply here. Wave-particle duality wasn't just about light either. Later experiments would show that matter, like electrons, neutrons, even whole molecules, also behaves this way, which means the strange split personality of light is actually the default personality of the universe. But before we bring matter into this mess, there's one experiment that truly burned wave-particle duality into the walls of physics forever, a return to Thomas Young's double-slit setup, but with a quantum twist. And what happened there would make even the calmest physicists spit out their coffee. Electrons as waves, ghost particles in your body. Remember Thomas Young's double-slit experiment with light? The one that proved light acts like a wave? Physicists in the 20th century thought, okay, light's weird, but matter, the stuff we're made of, surely follows the normal, predictable rules. Oh, sweet summer children, enter the electron, An electron is one of the basic building blocks of matter, the thing orbiting the nucleus of every atom in your body right now. It has mass, it carries electric charge, it can be trapped, accelerated, fired like a tiny bullet. If anything screams particle, it's an electron. So in the 1920s, some clever experimenters, and by clever, I mean slightly sadistic toward classical physics, decided to send a beam of electrons through the same kind of double-slit setup used in Young's light experiment. The expectation? You'd see two neat clusters on the screen behind the slits, like a pair of bullet holes. After all, these are particles. What they saw instead was the exact same kind of interference pattern you get from waves, bright and dark fringes. Electrons, particles of matter, were somehow behaving like ripples in a pond. This wasn't just a minor curiosity. It was a full-blown physics meltdown. It meant that every solid thing you can touch, your hands, your coffee mug, the entire chair you're sitting on, has a wave-like nature baked in at the most fundamental level. We just never notice it because for big objects, those waves are so absurdly tiny that they're effectively invisible. The wavy behavior only really shows up when the object is microscopic, like an electron. Louis de Broglie, a French physicist with a flair for bold ideas, proposed that everything has a wavelength, given by his now famous equation, wavelength equals Planck's constant divided by momentum. For an electron, that wavelength is measurable. For a baseball, it's so small it might as well be zero, which is why you don't see baseballs diffracting around goalposts. But here's where it gets even juicier. When researchers fired electrons one at a time through the double slits, the interference pattern still formed over time. Each electron seemed to interfere with itself, like it was somehow traveling through both slits at once, as a wave, and only deciding where to land when it hit the detector. It's the kind of thing that makes you stop and wonder whether the word particle is just a polite lie we tell ourselves. What's an electron then? It's not a little marble. It's not just a wave. It's something stranger. Something described by a wave function, a mathematical haze of probabilities. And remember, electrons aren't rare exotic objects. They're in every atom, flowing through every wire, bouncing around in your nervous system right now as you hear this. Which means this bizarre behavior isn't confined to labs. It's happening inside you all the time. But the real nightmare fuel for classical physics was yet to come. Because if electrons could be both particles and waves, what happens when you try to catch them in the act? What happens when you watch them choose a path? That question led to one of the most unsettling discoveries in all of science. The moment observation itself changed reality. The double-slit experiment, reality's mood swings. If science had a top 10 most embarrassing moments for classical physics list, this experiment would be number 1. We've already seen it in the 1800s with light, and just now with electrons. But here's the twist. It's not just about waves or particles anymore. It's about what happens when you try to watch. Let's recap the setup. You've got a source firing electrons toward a barrier with two thin slits. On the other side is a detector screen. If electrons were normal particles, like tiny bullets, they'd go through one slit or the other, and you'd see two neat clusters on the screen. If they were waves, you'd see the interference pattern, bright and dark bands as the waves overlap and cancel each other in certain places. We already know the shocking result. Electrons fired one at a time still build up an interference pattern over time. Somehow, each electron behaves like a wave, exploring both slits at once and interfering with itself. Weird, but okay, maybe that's just quantum nature doing its thing. Now comes the million-dollar question. What happens if you try to find out which slit the electron actually goes through? Surely if we just watch closely enough, we can catch it in the act. So physicists placed detectors at the slits, ready to record each electron's path. And then, poof, the interference pattern vanished. Instead of waves, electrons behaved like boring little particles again, landing in two clusters. Simply measuring which path they took destroyed the wave behavior. It was as if the electron had been keeping its options open. exploring both routes until it realized it was under surveillance and instantly chose one. The moment we observed it, the wave of probabilities collapsed into a single reality. You can spin this as poetic, observation creates reality, or keep it strictly scientific, measurement interacts with the system, changing its state. But either way, it's deeply unsettling. It suggests the universe doesn't have definite outcomes until something or someone forces it to decide. To make it stranger, if you remove the detectors, the interference pattern comes back. If you put the detectors in but don't look at the results, the interference stays gone, as if the act of recording is enough. Even when you try delayed choice experiments, deciding after the electron has passed the slits whether to measure its path, the results still respect your choice, as though time itself is negotiable. Physicists have been arguing over this for decades. Some, like Niels Bohr, embraced the shut-up-and-calculate philosophy, stop worrying about what's really happening, and just accept that the math works. Others, like Einstein, couldn't accept that reality is this flaky. He famously said, "I like to think the moon is there even if I'm not looking at it." The double-slit seems to suggest, maybe not. And here's the kicker. This isn't some fringe lab trick. The principle is baked into quantum mechanics itself. It's why quantum computers work, why particles behave probabilistically, and why we can never measure certain pairs of properties, like position and momentum, exactly at the same time. Which brings us to the next unavoidable question. Why can't we know everything? It's not about bad equipment or clumsy scientists. It's a fundamental law of the universe, one that Heisenberg turned into a simple, devastating principle that still haunts physics today. Heisenberg's uncertainty principle, why perfect knowledge is impossible. Imagine you're trying to take the perfect photo of a hummingbird in flight. You want two things, to know exactly where it is and exactly how fast it's moving. Simple enough, right? You crank up your camera's shutter speed. And sure, you freeze its position in razor-sharp detail, but now you have no clue how its wings are moving. Slow the shutter down to capture the blur of motion, and suddenly its position becomes a smudge. You can get one picture or the other, never both at the same time. That's essentially the Heisenberg uncertainty principle. Except instead of hummingbirds, we're talking about every particle in the universe. In 1927, Werner Heisenberg realized that quantum mechanics had a built-in limit to how much we can know. Not a technological limit, not a "we just need better tools" limit. A fundamental limit woven into the fabric of reality. The more precisely you know a particle's position, the less precisely you can know its momentum, which is basically its speed and direction. And the more precisely you know its momentum, the fuzzier its position becomes. It's not because particles are shy. It's because particles in quantum mechanics don't have definite values for both at the same time. They exist as a wave function, a spread-out cloud of probabilities. Measuring one property collapses the wave function in that dimension, but blows up the uncertainty in the other. If that sounds abstract, think about trying to measure an electron. To see it, you'd have to bounce light off it. But photons carry energy and momentum. The act of bouncing one off the electron inevitably changes the electron's speed or position. It's like trying to measure the exact location of a soap bubble by poking it with your finger. The measurement destroys the thing you're trying to know. Mathematically, Heisenberg's principle can be written as delta x times delta p is greater than or equal to h bar over 2, where delta x is the uncertainty in position, delta p is the uncertainty in momentum, and h bar is the reduced Planck's constant. That little inequality says, multiply the uncertainties together, and you can never get smaller than that magic number. There's no loophole. And it doesn't stop at position and momentum. There are other conjugate variables, like energy and time, that have their own uncertainty relationship. That's why we have phenomena like quantum tunneling, where particles borrow energy briefly to pass through barriers, then pay it back before reality notices. At first, this drove scientists mad. We like to think of the universe as a tidy machine. If you know the initial conditions well enough, you can predict everything forever. Laplace's demon, the mythical intellect that could calculate the future from the present, was officially unemployed. Instead, The quantum world is a casino where the dice aren't hidden under the table. They are the table. But here's the twist. The uncertainty principle isn't a bug. It's a feature. Without it, atoms wouldn't exist. Electrons would spiral into the nucleus, collapsing matter into a boring lump. The uncertainty in their momentum keeps them from falling in, giving us the stable atoms that make up, well, everything. So the next time someone says knowledge is power, remember, in quantum mechanics, there are hard limits to knowledge itself. We can predict probabilities with astonishing accuracy, but not certainties. And this probabilistic nature of reality isn't just philosophical. It has been tested, verified, and baked into our technology. And yet, even with this principle carved into the laws of physics, we still haven't hit the strangest part. Because there's a kind of connection between particles that makes the whole uncertainty business feel almost polite. A connection so bizarre, Einstein himself called it spooky action at a distance. And once you understand it, you'll never think of separation the same way again. Quantum entanglement, the spooky action that annoyed Einstein. If the uncertainty principle was a polite nudge that reality isn't what you think, quantum entanglement is a full-on slap across the face. It's the phenomenon that made Einstein squint at the math and mutter spooky action at a distance, which is physicist speak for, I don't like this one bit. Here's the setup. Imagine you have a pair of particles, electrons, photons, whatever, that interact in some way. Maybe they're created together in a single process, like two photons emitted from the same atom. When this happens, certain properties, like their spins, polarizations, or momenta, become linked, not just similar. Linked, they're now entangled. This means, if you measure a property of one particle, you instantly know the corresponding property of the other, no matter how far apart they are. Send one to New York and the other to Tokyo. Measure the New York one spin, and you instantly know the Tokyo one spin. Sounds harmless until you realize the twist. Before you measured them, neither particle had a definite value. They existed in a superposition, a fuzzy combination of possibilities. Measuring one doesn't just reveal its value. It forces it into a definite state and somehow forces the other distant particle into a corresponding state at the same moment. If that doesn't bother you, it should. Because if the effect is truly instantaneous, it seems to defy relativity's rule that nothing, not even information, can travel faster than light. Einstein hated this. In 1935, he, Boris Podolsky, and Nathan Rosen published a paper now known as the EPR paradox, arguing that quantum mechanics must be incomplete. They suggested there might be hidden variables, unknown local factors that determine the outcomes, restoring a nice, predictable reality. But in the 1960s, John Bell came along with Bell's theorem, a brilliant way to test whether hidden variables could explain entanglement. Experiments based on Bell's work showed over and over again, nope. The results violated what's called Bell's inequalities, meaning that no local hidden variable theory can match reality. The universe really is non-local in this specific, deeply weird way. So what's going on? There are a few ways to think about it. The mainstream Copenhagen interpretation says entangled particles are described by a single shared wave function. When you measure one, you collapse the wave function for both. The many worlds interpretation says there's no collapse. Instead, both outcomes happen, but you and your measurement device split into a version that sees one result and a version that sees the other. The pilot wave theory says there's a deeper, hidden structure guiding both particles in sync. Whichever explanation you pick, the experiments agree. Entanglement is real, it's measurable, and it's not just a lab curiosity. It's already the backbone of quantum cryptography, where two people can share a secret key encoded in entangled particles. And if anyone tries to eavesdrop, the entanglement is disturbed, revealing the intrusion. Here's the wildest part. Entanglement doesn't care about distance. Lab tests have shown it working across kilometers, with no degradation. And in principle, it could work across galaxies. But before you start texting your alien pen pal via entangled qubits, here's the bad news. You can't use it to send information faster than light. The results are still random. It's only when you compare notes later that the spooky correlation emerges. Still, the fact remains, once two particles are entangled, they remain parts of a single, unified system, no matter how far apart they drift. Space between them just doesn't seem to matter. And if that makes your head spin, wait until you hear what John Bell's experiments actually proved about reality, and how they forced physics to admit that the universe doesn't play by the local realism rule we once thought was sacred. Bell's theorem. Why there's no hiding from quantum weirdness. By the time John Bell entered the scene in the early 1960s, the debate over quantum entanglement had been stuck in the same circular argument for decades. Einstein had planted the flag for hidden variables, unseen, local rules that would restore the universe's common sense. Bohr and the Copenhagen crowd argued, in essence, nope, this is just how the universe works. Deal with it. Neither side had a knockout punch. Bell was the kind of physicist who didn't just complain about paradoxes. He wanted to turn them into testable experiments. So he asked a deceptively simple question. If hidden variables really exist, can we design a statistical test that quantum mechanics would fail, but a hidden variable universe would pass? The answer was yes. Bell worked out a set of inequalities, now called Bell's inequalities, that describe the maximum amount of correlation you could see between two separated particles if their properties were determined by local hidden variables. Think of it like a cheat detection algorithm. If the correlations in your measurements break the inequality, then local realism, the idea that particles have definite properties that aren't instantly influenced at a distance, is toast. The genius of Bell's idea is that it turned a philosophical argument into a concrete number you could check in the lab. It was no longer Einstein thinks this versus Bohr thinks that. It was, let's run the numbers and see which universe we live in. The first experimental tests came in the 1970s and 80s, notably by Alain Aspect in France. He set up pairs of entangled photons and measured their polarizations with detectors placed far enough apart that no signal, even at the speed of light, could connect them during the measurement. If hidden variables were pulling the strings, the results would stay within Bell's limit. Instead, they smashed right through it, matching the predictions of quantum mechanics and violating the inequalities by a clear margin. Over the years, experiments became more and more sophisticated, closing potential loopholes like detector inefficiency or the possibility that some information could sneak between the detectors. By 2015, multiple loophole-free Bell tests had been run. The result was the same every time: local realism is not compatible with our universe. That's a heavy sentence, so let's break it down. Local equals no faster than light influence. Realism equals the idea that physical properties exist with definite values before you measure them. Bell's theorem and the experiments that followed tell us, you can't have both. You have to give up at least one, and quantum mechanics forces you to give up realism, locality, or both. This is why Bell's work is so important. It didn't just confirm that entanglement is real. It showed that the universe fundamentally does not work the way our common sense and classical physics says it should. Einstein once said, "God does not play dice with the universe." Bell's theorem is like the dealer calmly raking in the chips, saying, actually, not only does God play dice, the dice are loaded and they're quantum entangled. Today, Bell's inequalities aren't just philosophical props. They're used to verify quantum devices, test quantum cryptography, and even push the boundaries of cosmology. Some researchers have used light from distant quasars to set detector choices, just to make sure the settings weren't somehow influenced locally. The verdict? Still quantum, still weird. And with the local realism rug officially pulled out from under us, physicists started to lean harder into using these bizarre correlations, rather than fighting them. Which brings us to something that sounds like science fiction but is very much real science. Quantum teleportation, where the properties of a particle can be transferred instantly from one location to another, without the particle itself making the trip. Quantum teleportation, not Star Trek, but close. If Bell's theorem made you feel like the universe was breaking its own rules, quantum teleportation is where it starts showing off. And no, we're not talking about beaming Captain Kirk onto an alien planet. Nobody's about to teleport your cat to Paris. But we can teleport a particle's state, its quantum identity, from one place to another without it physically traveling in between, which, in its own way, is even stranger. Here's the gist. First, you create a pair of entangled particles. Let's call them Alice's particle and Bob's particle. They could be photons, electrons, whatever your quantum lab has in stock. You send Alice's particle to, well, Alice, and Bob's particle to Bob. These two particles are now linked, no matter how far apart they are. Now comes the magic trick. Alice has another particle. One she wants to teleport to Bob. But remember, in quantum mechanics, you can't just look at the particle to see its full state. Measuring it directly would collapse its wave function and lose some of the information. So instead, Alice performs a special joint measurement on her particle and her half of the entangled pair. This measurement has a weird side effect. It instantly scrambles her particle's state into Bob's particle, no matter how far away he is. At that exact moment, Bob's particle becomes the particle Alice wanted to send. Spin, polarization, the whole quantum package, even though no physical thing traveled between them. The original particle? Gone. Its state has been destroyed in the process, thanks to something called the no-cloning theorem, nature's way of saying no copy-paste allowed. Of course, this doesn't break the speed of light. To complete the trick, Alice still needs to send Bob 2 bits of classical information, the result of her measurement, so he knows exactly how to adjust his particle. Only when those bits arrive can Bob's particle be turned into the exact twin of Alice's original. No faster than light texting, sorry. You might be wondering, why go to all this trouble? Because teleportation lets you move fragile quantum states across long distances without them getting wrecked by the environment. It's the backbone of plans for a quantum internet, where entanglement and teleportation could connect quantum computers around the globe with absolute security. The first real-world quantum teleportation happened in 1997 over about a meter. Today, scientists have done it over hundreds of kilometers, through fiber optic cables, and even between ground stations and satellites. Each time, it's the same eerie feeling, a particle here becomes a particle there, as if space didn't care. It's not Star Trek yet. You're not about to step into a shimmering beam and materialize at your friend's house, but it's a reminder that quantum mechanics isn't just theoretical weirdness. It's a toolbox we're starting to use. And one of the tools in that box? A trick that lets particles walk through walls without breaking a sweat. Quantum tunneling, the ghost trick that powers the sun. All right, time for one of my favorite "you've gotta be kidding me" moments in quantum physics. Quantum tunneling, it's the phenomenon that lets particles pass through barriers they have no business crossing, like walking through a locked door just because you felt like it. And if it didn't exist, the sun and you wouldn't be here. Let's start with the normal, everyday rules. In classical physics, if you want to get past a barrier, whether it's a hill, a wall, or a vault door, you need enough energy to climb over or break through. No energy, no crossing. Simple, logical, sensible. Which, of course, is why quantum mechanics completely ignores it. In the quantum world, particles aren't tiny billiard balls. They're waves of probability. Picture an electron approaching a wall. Classically, if it doesn't have enough energy to get over, it bounces back. But a quantum particle's wave function doesn't just slam to a stop at the wall, it leaks into it. And if the wall is thin enough, that leaked wave can continue on the other side, where the particle suddenly reappears. It's not that the particle drilled through. It was never in just one place to begin with. So part of it was always on the other side. If that sounds like cheating, it kind of is. Imagine throwing a tennis ball at a wall 1,000 times, and, once in a blue moon, it simply pops through to the other side without leaving a hole. That's tunneling. Here's the part that should make your jaw drop. Tunneling isn't rare in nature. It's everywhere. It's why nuclear fusion works inside the sun. Fusion requires atomic nuclei, positively charged, to get close enough to fuse. But positively charged things repel each other. At the sun's core temperatures, nuclei don't actually have enough classical energy to overcome that repulsion. They should just bounce off, yet they don't. Tunneling lets them slip past the energy barrier and merge, releasing the sunlight that keeps Earth alive. It's also at work in your everyday technology. The flash memory in your phone? It uses tunneling to move electrons through insulating layers. Scanning tunneling microscopes, the kind that can image individual atoms, literally rely on electrons tunneling between a needle tip and the sample. And here's a mind-bender: tunneling has no real classical equivalent. It's not about squeezing through a physical gap. It's about the fundamental nature of particles existing as spread-out probabilities. That spread-out nature gives them a non-zero chance of showing up on the forbidden side of a barrier. This leads to weird questions physicists still wrestle with. If a particle can tunnel through a barrier, how long does it take? Some experiments hint it might be instantaneous. Others suggest it's finite, but strangely short, almost as if the particle takes a shortcut outside normal space-time. And if you want a sci-fi twist, tunneling means there's always a tiny, ridiculously tiny chance that your atoms could rearrange themselves and you'd find yourself somewhere else without crossing the space in between. No, it won't happen in your lifetime, or in a million lifetimes. But the math doesn't forbid it. Which means the universe has no absolute rule against ghost walking. It just makes it absurdly improbable. So the next time you see sunlight, you're looking at the result of a quantum jailbreak, particles ignoring the most basic rules of energy and motion. And speaking of particles breaking rules, wait until you meet the rest of the quantum cast, the bizarre zoo of particles, fields, and forces that make up everything you've ever seen. Meet the particles, photons, quarks, gluons, and friends. Welcome to the smallest petting zoo in the universe, the standard model of particle physics. It's not big. In fact, it's ridiculously small. But this tiny collection of species accounts for everything you've ever seen, touched, eaten, or thought about. And it's weird. Let's start with the photons. These are the rock stars of the particle world. They're the quanta of light, tiny packets of electromagnetic energy. They carry no mass, travel at the speed of light, because, well, they are light, and they never slow down. Photons are how you see everything, bouncing off objects into your eyes. They also carry the electromagnetic force, which holds atoms and molecules together. Basically, without photons, you'd be blind, cold, and floating in a very lonely void. Now meet the quarks, the building blocks of protons and neutrons. They come in 6 flavors: up, down, charm, strange, top, and bottom. Yes, those are the real names, and no, physicists were not drunk when they came up with them, probably. Protons are made of 2 up quarks and 1 down quark. Neutrons are 1 up quark and 2 down quarks. The other flavors? They pop up in high-energy environments like particle accelerators or cosmic rays, then quickly decay into the more boring up and down types. Quarks are never found alone. They're always locked together in groups. Why? Enter the gluons. These are the sticky particles that hold quarks together inside protons and neutrons. If photons are the messengers of electromagnetism, gluons are the enforcers of the strong force, the strongest interaction in nature. The name is perfect. Imagine if superglue had a personal vendetta against letting anything drift apart. Then we have the leptons, a family that includes the humble electron. Electrons are the glue between the nucleus and the rest of the atom, orbiting in quantum clouds. They're also responsible for electricity, chemistry, and the fact that your chair doesn't let you fall through it. In the lepton family, you'll also find the muon, a heavier, short-lived cousin of the electron, and the tau, even heavier, even shorter-lived. And each of these has a neutrino buddy, ghost-like particles that barely interact with matter at all. Billions of neutrinos are streaming through your body every second, and you'll never feel them. Finally, there's the boson crew, the force carriers. We already met photons and gluons. The W and Z bosons are responsible for the weak force, which governs radioactive decay. They're heavy, short-lived, and play a starring role in the nuclear processes that power stars and nuclear bombs. And then there's the Higgs boson, the particle that proves the existence of the Higgs field, which gives mass to other particles. Think of the Higgs field as invisible molasses spread across the universe. Particles moving through it get dragged just enough to gain mass. The beautiful and slightly unnerving thing about the Standard Model is that it's a complete set for everyday matter and forces, gravity excluded. All the diversity of the universe, stars, galaxies, oceans, your dog, comes from different arrangements of these few basic particles and the forces between them. It's like building every book in the world from just 26 letters. If those letters occasionally exploded, tunneled through walls, or existed in two states at once. But here's the thing. Knowing the cast is just the start. The real story is the stage they perform on. The quantum fields that permeate everything. The invisible ocean in which particles are just ripples. And if you thought the particles were strange, wait until you see the stage. The Higgs field, the invisible molasses that gives mass. If you've ever tripped over the phrase Higgs boson in the news and thought, that sounds important, but I have no idea what it is, you're not alone. When it was finally detected in 2012, the headlines called it the God particle, a nickname most physicists hate, by the way, and treated it like the missing piece of a cosmic puzzle. Which, to be fair, it kind of is. Here's the problem the Higgs boson solved. In the Standard Model, we've got our list of particles, electrons, quarks, and all their weird cousins. But when you first write the equations that describe them, they come out massless. They all behave like photons, zipping around at the speed of light. Which is a slight issue because massless particles can't slow down, clump together, or form atoms. So how do we get from that sterile, massless world to one with stars, planets, and coffee mugs? Enter the Higgs field. Think of it as an invisible energy field that exists everywhere in the universe. Yes, even in the empty space between galaxies. It's not a force like gravity or electromagnetism. It's more like a background texture to reality. When certain particles move through this field, they interact with it, and that interaction gives them mass. Like swimmers feeling resistance as they move through water. The stronger the interaction, the more mass they have. If they don't interact at all, they stay massless, like the photon. A classic analogy is the celebrity at a party model. Imagine the Higgs field as a crowded room full of people. A famous actor walks in, and instantly a dense cluster of partygoers crowds around them, slowing their movement. That's a particle with a lot of mass. A lesser-known guest slips through barely noticed. That's a lighter particle. And someone totally unknown drifts through without a single person stopping them. That's a massless particle. The Higgs boson itself is a ripple in this Higgs field, the way a photon is a ripple in the electromagnetic field. Detecting the boson was the proof that the field is real. It's like finding a single drop of water that confirms the existence of the entire ocean. Finding it wasn't easy. The Large Hadron Collider, LHC, that 27-kilometer underground ring near Geneva, was basically built for this job. Physicists smashed protons together at energies high enough to momentarily disturb the Higgs field and produce a Higgs boson. But the boson is unstable. It decays into other particles almost instantly. So researchers had to detect the debris, reconstruct the event, and match it to the predicted Higgs signature. When they finally did, in July 2012, it was champagne all around. Why does this matter to you? Because without the Higgs field, mass wouldn't exist. And without mass, there would be no atoms, no chemistry, no planets, no life. The entire universe would be an eternal soup of massless particles rushing through empty space, never forming anything. The Higgs field is part of a bigger truth we'll keep coming back to. Particles aren't just little dots in space. They're excitations, ripples, in underlying fields that stretch across the entire cosmos. And if the Higgs field is the molasses that gives mass, then the other quantum fields are the invisible ocean in which all reality swims. And speaking of oceans, next we're going to wade into the one field that underlies all of this, the quantum fields themselves, the true stage on which the entire particle zoo dances. Quantum fields, the ocean in which particles swim. By now, we've met the cast of the subatomic world, the particles, and even peeked at the Higgs field. the strange, invisible molasses that gives some of the mass. But here's the plot twist. Those particles we've been talking about, they're not the most fundamental thing. They're not even the things you think they are. In modern physics, particles are more like ripples. The real stars of the show are quantum fields. Think of the universe as being filled, completely and everywhere, with invisible fields. Each type of particle has its own field. There's an electron field, a photon field, a quark field, and so on. These fields aren't in space, they are space. They're the underlying fabric that stretches across the entire universe. A particle is just a localized excitation, a little ripple in one of these fields. It's like throwing a stone into a calm pond. The ripples you see are disturbances in the water. But the pond itself was always there. Without the pond, no ripples. Without the field, no particles. Here's where it gets even more surreal. These fields don't turn off when nothing's happening. Even in empty space, they're constantly fluctuating, bubbling with what's called vacuum energy. Quantum mechanics says you can never have a field with absolutely zero energy. There's always a jitter, a quantum hum in the background. And these jitters can briefly summon virtual particles into existence, ghost-like entities that pop in, interact, and vanish almost instantly. This ocean of fields perspective explains why particles can appear and disappear, why forces work across empty space, and why nothing in the quantum world is ever truly still. It also makes sense of why the laws of physics are the same everywhere. The fields stretch across the whole universe, so the rules embedded in them apply everywhere. Now, the moment you buy into the field's first, particle's second idea, some weird consequences fall into place. Forces are just interactions between fields. The electromagnetic field interacts with the electron field, the gluon field interacts with the quark field, and so on. Mass comes from interactions with the Higgs field. No Higgs interaction, no mass. Empty space isn't empty. It's a restless, fluctuating soup of field energy. If you want a mental image, picture all of reality as a giant three-dimensional ocean that extends infinitely in every direction. Every point in space is saturated with multiple invisible fluids, one for each particle type, overlapping without mixing. When you see a particle, you're seeing a tiny ripple racing through just one of those fluids. The truly wild part? This isn't just a philosophical model. The math of quantum field theory, QFT, the framework that treats particles as excitations of fields, is the most accurate predictive machine in science. It can calculate the magnetic moment of the electron to a precision of more than 10 decimal places, and the experimental results match exactly. That's like predicting the distance between New York and Los Angeles down to the width of a human hair. Quantum fields aren't just a nice way to think about things. They're the most precise description of reality we've ever had. And yet, they leave us with big, unanswered questions. Like, if every point in space is buzzing with vacuum energy, why doesn't that energy curve space-time into a microscopic black hole? That's one of the greatest unsolved problems in physics, the cosmological constant problem, and it's a headache for another day. For now, what matters is this. The universe isn't made of particles sitting in empty space. The universe is made of space that is never empty, a restless ocean of invisible fields. Particles are just the waves. And within this ocean, there are ripples so fleeting you might miss them entirely, except their effects are everywhere. These are the virtual particles, the blink-and-they're-gone ghosts of the quantum world. Virtual particles, blink and you miss them matter. If particles are the real ripples in quantum fields, then virtual particles are the ghosts. They're not permanent, you can't pin them down, and yet they leave fingerprints all over the universe. And here's the kicker. Without them, much of what you take for granted, including you, wouldn't exist. Let's get one thing straight right away. When physicists say virtual particle, they don't mean a tiny thing floating around in space that you just can't quite see. They mean a temporary disturbance in a quantum field that pops into existence, does something, and then disappears so quickly that it never becomes a real particle in the sense we can directly detect. It's like a magician's assistant who appears just long enough to hand over a prop and then vanishes behind the curtain. Here's the rule book that makes this possible. The Heisenberg uncertainty principle doesn't just apply to position and momentum, it also applies to energy and time. The more briefly something exists, the more wiggle room it has in energy. For an incredibly short time, a field can borrow energy to create a particle-antiparticle pair, as long as that energy is paid back before the universe notices. Think of it like quantum credit card fraud, except the charges always get reversed instantly. This happens constantly. Even in the vacuum of space, quantum fields are bubbling with these ghostly pairs, an electron and a positron, a quark and an antiquark, appearing and annihilating in a flash. You might think, well, if they're here and gone so fast, who cares? But the effects are measurable. They can shift the energy levels of electrons in atoms, the Lamb shift, alter the magnetic moment of particles, and even change the force between charged particles. One of the most mind-blowing examples of virtual particles at work is the Casimir effect. Put two uncharged metal plates extremely close together in a vacuum. Quantum theory says the space between them will have slightly fewer virtual particles than the space outside, because only certain wavelengths fit between the plates. That imbalance creates a tiny pressure that pushes the plates together. No springs, no magnets, just the restless activity of the quantum vacuum giving a gentle shove. And virtual particles aren't just sitting around being cute physics trivia, they're the messengers of the forces between particles. When two electrons repel each other, you can describe that mathematically as them exchanging virtual photons. Quarks exchange virtual gluons to stay locked inside protons and neutrons. The weak nuclear force operates via virtual W and Z bosons. In quantum field theory, every interaction, every push and pull is the result of virtual particles flitting back and forth, doing their work in the blink of an eye. Now, here's the part that bends your brain. Virtual particles aren't less real than regular particles just because they vanish quickly. In the equations, they're every bit as crucial. They just don't obey the usual energy-momentum relationship that real particles have, which is why they can't be detected directly. They're like the backstage crew in a theater. You never see them, but without them, the show doesn't happen. And if you zoom out far enough, this buzzing sea of virtual particles may even connect to some of the biggest mysteries in cosmology, like dark energy, the force causing the universe's expansion to accelerate. One theory says dark energy might just be the net effect of all this quantum vacuum activity. If that's true, it means the ghosts of the quantum world are literally shaping the fate of the cosmos. So the next time someone says nothing is happening, remember, in physics there is no nothing. Even the emptiest corner of space is a crowded party, full of guests who never stay long enough to be introduced. And speaking of parties, our next stop isn't about the guests. It's about the entertainment. Let's see what happens when all this quantum weirdness gets turned into practical magic, the kind that makes your phone, your computer, and your entire modern life possible. Lasers and LEDs, everyday magic from the quantum. Here's a fun game. Pick up your phone and stare at it for a moment. There's a good chance you're looking directly at quantum physics in action. Not in some sci-fi experiment or billion-dollar lab, but in the tiny glowing pixels of your screen. Yep, lasers and LEDs, the flashy, colorful toys of modern tech, are pure quantum wizardry hiding in plain sight. Let's start with LEDs, light-emitting diodes. At first glance, they're nothing glamorous. They're basically microscopic sandwich cookies made of special materials called semiconductors. When you push an electric current through that sandwich, electrons and their positively charged counterparts, called holes, meet up and, how to put this politely, annihilate each other. But they don't go quietly. When an electron falls into a hole, it drops from a higher energy level to a lower one, and the leftover energy escapes as a photon, a particle of light. The color of that light depends on the size of the energy drop, which depends on the semiconductor's properties. Change the material, change the color. That's why your TV can give you both deep, cinematic blues and suspiciously neon greens. This is the photoelectric effect in reverse. Einstein got a Nobel Prize for explaining how light can knock electrons out of a material. LEDs flip that idea, shove electrons into a material, and out comes light. Same quantum rules, just running the process backwards. Now for lasers. Forget the movie cliches of red beams slicing through bank vaults. The real magic is in how lasers produce light that's absurdly well-behaved. Normal light is chaotic. Photons shoot out in all directions, with all sorts of wavelengths. A laser, on the other hand, is the definition of discipline. Every photon has the same wavelength, the same phase, and they all march in lockstep like a perfectly trained army. How do you get light to behave like that? You start with something called stimulated emission, another Einstein contribution, because apparently he wasn't busy enough revolutionizing physics elsewhere. You take atoms or molecules and pump them full of energy, so their electrons jump to higher levels. Then you give one of them a little nudge, a photon of just the right wavelength. When an excited electron drops back down, it emits a photon. And here's the trick, that new photon is a perfect clone of the original. Same direction, same wavelength, same phase. And that photon can go trigger another one, and so on, creating a chain reaction. The result? A coherent beam of light that can travel ridiculous distances without spreading out much. Lasers are everywhere. They read the Blu-ray discs you forgot you owned. They measure distances with millimeter precision. They weld steel. They fix your eyesight. They scan your groceries. They bounce off mirrors on the moon so we can measure the Earth-Moon distance to within a centimeter. And if you've ever used a barcode scanner, had laser hair removal, or annoyed a cat with a red dot, congratulations, you've been part of the quantum laser fan club. Here's the best part, both LEDs and lasers rely on one core idea. Energy levels in atoms are quantized. Electrons can't have just any amount of energy. They have to be in specific states, and when they change states, they release or absorb photons of very specific energies. This is the same quantum ladder we've been talking about since Planck and Einstein kicked off the revolution over a century ago. So next time you scroll TikTok, watch Netflix, or play with your dog and a laser pointer, remember, you're using the exact same quantum rules that power atomic clocks, particle accelerators, and the very fusion reactions in the sun. You're not just holding technology, you're holding a domesticated piece of quantum physics. And we're not done with the everyday magic yet. Because hiding inside your car's navigation system, your phone's Maps app, and every airplane's autopilot is another quantum trick, one that depends on both relativity and the subatomic world working together. Without it, your GPS would be so wrong you'd miss your own driveway. GPS and relativity, why satellites use both Einstein and quantum. Here's a fun thought experiment. Take away quantum physics and Einstein's relativity, and your GPS would be so bad it couldn't even find your city, let alone your street. It would be like asking a drunk pirate for directions using a 300-year-old treasure map. We treat GPS as this boring, everyday thing. Tap your phone. Blue dot appears. You go where it tells you. But that little blue dot is the end result of some of the most extreme physics humans have ever mastered. How GPS actually works is deceptively simple. About 30 satellites orbit Earth, each carrying an extremely precise atomic clock. Your phone listens to signals from at least 4 of them. By measuring how long each signal takes to reach you, your phone calculates your distance from each satellite. Do that math for 4 or more satellites at once, and boom, your position pops up on the map. Sounds straightforward, right? Except here's the problem. GPS relies on time being incredibly precise. And in physics, time is not the universal metronome we thought it was in the 1800s. Time is stretchy. It changes depending on speed and gravity. And satellites have both of those issues in spades. First, there's special relativity, Einstein's rule that moving clocks run slower. GPS satellites orbit at about 14,000 kilometers per hour, so their onboard clocks tick slightly slower than clocks on Earth. If we didn't correct for that, your GPS location would drift by several kilometers every day. Then there's general relativity, Einstein's other bombshell, which says that clocks in weaker gravity tick faster. Since GPS satellites are about 20,000 kilometers above Earth's surface, gravity is weaker for them than it is for you on the ground. That means their clocks run faster compared to ours. Here's the kicker. These two effects pull in opposite directions. Special relativity makes the satellite clocks tick about 7 microseconds slower per day, General relativity makes them tick about 45 microseconds faster per day. Net effect? Satellite clocks run about 38 microseconds faster than Earth clocks, and that's enough to throw your GPS off by about 10 kilometers per day. So GPS engineers do the most unromantic thing possible. With Einstein's mind-blowing theory, they pre-adjust the satellite clocks before launch so that once they're in orbit, they tick in sync with ours. It's like buying shoes one size too small because you know they'll stretch. Now, where does quantum physics come in? Those atomic clocks on the satellites, the ones that need to be so accurate they lose less than a billionth of a second per day, are pure quantum tech. They work by measuring the natural ticking frequency of electrons jumping between energy levels in atoms like cesium or rubidium. These transitions are perfectly regular, making them the most reliable clocks we've ever built. So every time you get turn-by-turn directions to your favorite taco place, you're using Einstein's relativity to fix the timing, and quantum mechanics to measure the timing in the first place. It's like your phone is running a miniature physics lab every time you ask it not to get you lost. The next time someone says relativity and quantum physics don't matter in real life, feel free to point out that without them, their GPS would think they were somewhere in the next town over, or possibly in the middle of the ocean. And speaking of the future of navigation, what happens when we ditch GPS entirely and replace it with something even stranger? That's where quantum computing, quantum cryptography, and the next generation of quantum tech come into play. Quantum computing, brains made of qubits. If classical computers are like the dependable accountants of the tech world, neat, logical, and a little boring, then quantum computers are the rock stars who can solve the impossible, but might also spontaneously set their guitar on fire. And someday, they might make your current laptop look as outdated as a pocket calculator from 1975. Let's start with the computers you know. A classical computer stores information in bits, which can be either a 0 or a 1. Every app you've ever used, every cat video you've ever streamed, is ultimately a massive collection of bits flipping between those two states billions of times per second. It's binary, simple, reliable, boring, but it works. A quantum computer, on the other hand, uses qubits. And qubits are different. Thanks to quantum superposition, a qubit can be 0, 1, or both at the same time until you measure it. It's like flipping a coin and having it be both heads and tails in midair. Now imagine you flip not one, but dozens, hundreds, or thousands of these quantum coins, and their states are all linked by entanglement, meaning changing one affects the others instantly. That's when the magic or madness happens. Why does this matter? Because a quantum computer can process an astronomical number of possibilities in parallel. A classical computer trying to solve a complex problem has to check possibilities one by one. A quantum computer can explore a massive range of them simultaneously, thanks to superposition and entanglement. That means certain problems, like factoring huge numbers, hello, encryption, simulating complex molecules, hello, new medicines, or optimizing massive systems, hello, shipping routes, weather forecasting, and AI training, could be solved in seconds instead of centuries. But before you throw your MacBook out the window, here's the reality check. Quantum computers aren't ready to run your Spotify playlist. They're delicate. Qubits are absurdly sensitive to their environment. Heat, vibration, stray electromagnetic fields, and any disturbance can cause them to lose their quantum state, a problem known as decoherence. It's like trying to balance a pencil on its tip in the middle of an earthquake while someone's blowing on it. This fragility is why most quantum computers today live in giant, shiny, sci-fi-looking refrigerators cooled to a fraction of a degree above absolute zero. They need that extreme cold to keep qubits stable long enough to perform calculations. Even then, error correction is a nightmare. Quantum systems can produce answers, but those answers have to be filtered through mountains of correction algorithms to be reliable. Still, progress is happening. Companies like Google, IBM, and startups you've never heard of are racing to scale up from tens of qubits to thousands, then millions. In 2019, Google claimed quantum supremacy, demonstrating that their quantum machine solved a specific problem in minutes that would take the best supercomputer thousands of years. Was it a problem anyone cared about in the real world? Not really, but it was proof that quantum computers can do something classical computers simply can't. And here's where the light sarcasm comes in. The day quantum computers are practical, most of our current encryption systems, the ones protecting your bank account, your medical records, and the password you swore you'd never reuse, could be toast. That's why quantum cryptography, which we'll get to soon, is already being developed as a defense before the offense fully exists. Quantum computing isn't just, quote, faster computers. It's a completely different way of thinking about information, one where uncertainty is a feature, parallel universes of possibilities are your workspace, and the line between physics and computation vanishes. And while they might never replace your phone or your home PC, they'll almost certainly become the engines that solve problems too big for anything else. And that includes the technology to keep secrets safe, in a world where your old encryption would last about 5 seconds. Speaking of keeping secrets, let's talk about quantum cryptography, where physics itself, not just math, is the lock on the door. Quantum cryptography, unbreakable codes. Let's be honest. Most people's approach to cybersecurity is hope for the best and use the same password everywhere. But the people who actually build secure communication systems, they live in a paranoid world where every email, every financial transaction, every whispered government secret is assumed to be under attack. And in that world, quantum cryptography isn't just cool science. It's the ultimate insurance policy. The basic idea is almost too good to be true. Use the laws of physics themselves to make eavesdropping impossible. Not really hard. Not would take a supercomputer 10,000 years. Impossible. If someone tries to spy, the very act of listening changes the message and exposes them instantly. Here's how it works. At the heart of quantum cryptography is a technique called quantum key distribution, QKD. The goal isn't to send the actual message via quantum means. That part still goes over normal channels. Instead, QKD creates a shared secret key between two people. Let's call them Alice and Bob, because apparently physicists don't know any other names. This key is what they'll use to encrypt and decrypt their real messages. To set up the key, Alice sends Bob a stream of photons, each prepared in one of several possible quantum states, maybe polarized horizontally, vertically, or at an angle. Thanks to quantum mechanics, each photon's exact state can't be measured without disturbing it. If an eavesdropper, Eve, because of course she's called Eve, tries to intercept the photons, she has to guess the correct way to measure them. And because guessing wrong alters the state, Bob will detect discrepancies when he compares notes with Alice over a public channel. If they see too many errors, they know Eve's been snooping, and they throw the key away. That's the genius of it. The security isn't based on math that might someday be broken by quantum computers. It's based on the unbreakable rule from the quantum world. You can't measure something without changing it. QKD has already moved from the lab into the real world. Banks have tested it to secure financial transactions. The Chinese satellite Mikius demonstrated quantum key distribution between Beijing and Vienna in 2017, sending encryption keys via photons across 200 kilometers. And there's serious talk about building a quantum internet, a global network where every link is protected by quantum keys, making wiretapping a quaint relic of the past. Of course, there's a catch. Quantum communication is still fragile. Photons get lost in fiber optic cables over long distances, and sending them through the air means dealing with weather, clouds, and the occasional curious pigeon. Quantum repeaters, devices that can extend these secure links without breaking the quantum rules, are still in development. So for now, QKD is more like a high-security vault used for very special cases, not your everyday Gmail login. Still, the implications are huge. Once the infrastructure is in place, even the most powerful future quantum computers won't be able to brute force these keys. Because in quantum cryptography, you're not just relying on human cleverness, you're relying on the universe itself to tattle on anyone who tries to cheat. And speaking of the universe, quantum tricks aren't just hiding in our technology, they're hiding in life itself, which is where things start getting even stranger, because nature has been doing quantum magic long before we built our first lab experiment. Quantum biology, life's hidden quantum tricks. When people hear quantum mechanics, they imagine particle accelerators, cryogenic labs, and scientists in clean suits. Nobody pictures a sunflower, or a robin, or their own nose. But nature's been running quantum experiments for billions of years, long before we figured out how to plug in a laser. This is the strange new field of quantum biology, where life itself hijacks quantum effects to do things that would be impossible under plain old classical physics. And yes, it's exactly as weird as it sounds. Let's start with photosynthesis. You know the drill. Plants take sunlight, water, and carbon dioxide, and turn them into sugars and oxygen. Simple, right? Except it's not. The first step in photosynthesis is capturing a photon, a particle of light, and shuttling its energy to the reaction center in the plant cell where chemistry happens. This energy transport has to be ridiculously efficient because the energy from a single photon is tiny and fragile. Classically, you'd imagine the energy bouncing randomly from molecule to molecule like a drunk tourist trying to find the hotel. But experiments show it moves through the plant's light-harvesting complex almost perfectly, as if it already knows the best route. How? Quantum coherence. The same principle that lets a qubit exist in multiple states. The energy doesn't take one path. It explores all possible paths at once, then interferes with itself so that the wrong paths cancel out, leaving only the fastest, most efficient route. It's like having Google Maps preloaded in the photon's brain. Then there's bird navigation. Many migratory birds, like European robins, can sense Earth's magnetic field to navigate thousands of kilometers. For years, we didn't know how. Now, the leading theory is that they have a special protein in their eyes called cryptochrome that forms a pair of entangled electrons when hit by light. The orientation of Earth's magnetic field affects the quantum spin state of these electrons, which in turn influences chemical reactions in the bird's vision system. Translation: robins might literally see magnetic fields as part of their visual landscape. Nature gave them a built-in heads-up display with entanglement as the operating system. And then there's your sense of smell. The classic idea is that smell works like a lock-and-key system. Odor molecules fit into receptors like puzzle pieces, but that doesn't explain why some molecules with the same shape smell totally different. A competing theory says smell might also depend on quantum tunneling. When an odor molecule binds to a receptor, electrons in the receptor might tunnel through the molecule if its bonds vibrate at just the right frequency. Different molecules vibrate differently, and your nose may be detecting those quantum vibrations. If true, you're literally sniffing quantum behavior every time you walk past a bakery. Quantum biology isn't without controversy. Some scientists argue these effects are fleeting, and warm, messy biological systems can't maintain quantum coherence long enough to matter. Others point out that evolution had billions of years to stumble upon hacks that we're only now starting to understand. And honestly, nature doesn't care whether we think something should be possible. It just does it. What's certain is that quantum mechanics isn't confined to the cold, pristine vacuum of a lab. It's woven into the machinery of life itself. Every time you breathe, eat, see, or move, you may be riding on quantum effects without even knowing it. And that blurs a line we thought was clear, the one between the living world and the subatomic world. Because if quantum rules apply to plants, birds, and maybe your nose, then maybe they apply to bigger, stranger systems too. And that brings us to the part of quantum physics that stops being about biology or technology and starts being about the very nature of reality itself. Schrödinger's cat, the sarcastic thought experiment that became a meme. If you've spent more than 5 minutes on the internet, you've probably seen a t-shirt or coffee mug that says something like, "Schrödinger's cat is alive and dead." It's one of those physics references that escaped the lab and ran wild in pop culture. But here's the twist. Erwin Schrödinger didn't invent his cat to explain quantum mechanics. He invented it to mock it. The year was 1935. Quantum theory was already weird enough to give Einstein migraines. One of its most unsettling features was the idea of superposition. A particle can exist in multiple states at once until it's observed. Only then does the wave function collapse into a definite state. Niels Bohr and the Copenhagen interpretation crew basically shrugged and said, yep, that's how it works. Schrödinger wasn't convinced. He thought the whole observation business was ridiculous if you took it literally. So he decided to crank the absurdity dial up to 11. Here's the setup. Put a cat in a sealed box with three things: a tiny bit of radioactive material, a Geiger counter, and a vial of poison gas. The radioactive material has a 50% chance of decaying within an hour. If it decays, the Geiger counter detects it, triggers a mechanism, and breaks the vial, killing the cat. If it doesn't decay, the cat lives. Now, according to quantum mechanics, until you open the box and check, the atom is in a superposition of decayed and not decayed. And because the cat's fate depends on the atom, the cat should also be in a superposition, alive and dead at the same time. Ridiculous, right? That was the point. Schrödinger was trying to show that blindly applying quantum rules to everyday objects leads to nonsense. The cat paradox was meant as a critique, not a literal instruction manual for feline cruelty. But the more people thought about it, the less ridiculous it seemed. If quantum mechanics is the true rulebook of the universe, then in principle it applies to everything: cats, people, planets. The only reason we don't see superpositions in our everyday lives might be because of decoherence, the process by which interactions with the environment force a quantum system into a definite state almost instantly. Your cat doesn't stay alive and dead because it's constantly observed by air molecules, photons, and every other particle in its environment. Still, the Schrödinger's cat thought experiment has become a kind of gateway drug for quantum weirdness. It's an easy way to explain to non-physicists that the quantum world doesn't follow common sense, at least not the kind you'd trust to walk your dog. The irony is that Schrödinger's cat outlived Schrödinger's original intention. He wanted to highlight a problem. Instead, he gave the world a mascot. A sarcastic jab at quantum mechanics became the most famous animal in physics. And the cat is more than a meme. It's a stepping stone to deeper questions. If a quantum system can hold multiple realities until observed, what does that say about the role of the observer? Does reality depend on measurement? Or does it split into multiple versions where every outcome happens? That last question leads us straight to one of the most provocative ideas in all of science, the many worlds interpretation. And if Schrödinger's cat makes you uneasy, wait until you find out that in many worlds, there's a universe where it's alive, another where it's dead, and another where it's plotting revenge. Many worlds, infinite versions of you. Schrödinger's cat left us with a nasty question. When a quantum system is in superposition, multiple states at once, and we observe it, what actually happens? The Copenhagen interpretation says the wave function collapses into a single reality. Poof! All the other possibilities vanish. Neat, tidy, and deeply unsatisfying to anyone who doesn't like magic wands waved over the laws of physics. In 1957, a young physicist named Hugh Everett III had a different idea. What if the wave function never collapses at all? What if all the possible outcomes of a quantum event happen just in separate, non-communicating realities? Open Schrödinger's box, and in one universe the cat is alive, in another it's dead. Both outcomes are real. You just happen to find yourself in one of them. This is the many worlds interpretation, and if you follow it to its logical conclusion, it means the universe is constantly splitting into versions for every possible quantum event, every coin flip, every particle decay, every neuron firing in your brain. Each choice, each random event spawns a branch of reality. Sounds like science fiction, right? It is. And it isn't. Mathematically, many worlds is just quantum mechanics without the extra collapse rule. It keeps the equations clean, removes the need for a special observer, and treats the whole universe as one giant wave function evolving smoothly over time. Of course, the price for that elegance is infinity. An infinity of branching timelines. An infinity of views. Somewhere there's a version of you who decided not to watch this video. Somewhere else there's a version who dropped out of school and became a goat farmer. And somewhere, brace yourself, there's a version who still thinks pineapple belongs on pizza. The idea is seductive because it solves the quantum measurement problem without breaking the math. But it's also unsettling because it makes you question what you even means. If there are countless copies of you, each living out a different history, is any one of them the real you? Or are you just one branch in a sprawling cosmic fractal? Critics of many worlds argue it's untestable. If we can't interact with these other universes, how do we know they're there? Supporters counter that Copenhagen is just as untestable in a direct sense, and at least many worlds doesn't require physics to behave differently when you're looking versus when you're not. And here's the kicker. Many worlds isn't just philosophical hand-waving anymore. In quantum computing, for example, the math works as if the computer is performing calculations across multiple branches of reality in parallel, before combining the results in our branch. Whether those branches are real or just a useful model is an open question, but the technology doesn't care. In the end, many worlds is like a mirror. It reflects back your own tolerance for weirdness. If you crave a single definite universe, you might hate it. If you're okay with infinite cosmic branching, it's oddly comforting, because in some branch, you've made every right choice, won every lottery, and never once sent a text to the wrong person. But if you thought that was a big swing, wait until you hear about an interpretation that tries to bring quantum physics back to something more deterministic, something that looks at first glance like it could make quantum mechanics normal again, until you realize it's hiding its own brand of weirdness. Pilot wave theory, the hidden reality hypothesis. By now, you've seen how quantum mechanics has a knack for making reality feel like a choose-your-own-adventure gone wrong. The Copenhagen interpretation says, stop asking what's really happening. The math works. Just calculate and move on. Many worlds says, everything happens, all the time, in infinite branching universes. But what if you're not ready to live in a multiverse, or accept reality as a magician who refuses to explain the trick? That's where pilot wave theory strolls in, with a swagger and a, see, we can make this sane again attitude. Its promise? Quantum mechanics with a clear, definite reality, no collapse, and no need for infinite universes. The catch? It's got its own flavor of strange. The idea actually predates Copenhagen. In 1927, physicist Louis de Broglie proposed that every particle is accompanied by a guiding wave, a pilot wave, that tells it exactly where to go. Think of it like a surfer, the particle, riding an invisible wave, the pilot wave, that stretches across space. The wave evolves according to the Schrödinger equation, the same math used in regular quantum mechanics, but the particle's position is always well-defined, whether you measure it or not. No fuzzy superposition, no both here and there. It's always somewhere, so why don't we just all agree this is better and go home? Because the pilot wave has a few quirks that make it just as unsettling in its own way. For starters, the wave isn't confined to the particle's location. It can extend across vast distances instantly. In fact, in a double-slit experiment, the particle goes through one slit, but the pilot wave goes through both, creating the interference pattern. So you still get all the weirdness of quantum effects, just hidden behind the scenes. Here's the part that would have made Einstein spit out his coffee. Pilot wave theory is non-local, meaning the wave guiding one particle can instantly be affected by something happening to another particle far away. Sound familiar? Yep, it's the same spooky action from entanglement. So even though pilot wave theory gives particles definite positions, it can't escape the weird faster-than-light influence problem. For decades, Copenhagen's shut-up-and-calculate attitude steamrolled de Broglie's idea. It wasn't until the 1950s that physicist David Bohm revived it, polishing the math and showing it could match all the predictions of standard quantum mechanics. Since then, it's been called de Broglie-Bohm theory, or just Bohmian mechanics. The appeal? It restores determinism. Given the exact starting conditions, you could, in principle, predict the future exactly. It says there's an underlying reality, not just probabilities. It removes the weird observer role. particles don't care if you're looking. The drawbacks? It requires this invisible, all-encompassing pilot wave that instantly connects distant points in space. That non-locality isn't just inconvenient. It clashes with relativity's no faster than light rule in ways that make physicists twitch. And like all interpretations of quantum mechanics, it's not directly testable against Copenhagen. They make the same predictions for every experiment we can do. So pilot wave theory ends up in a strange spot. It's a comforting alternative for people who hate collapse and many worlds. But it's also a reminder that any explanation of quantum mechanics is going to feel weird, because the universe is, apparently, a weirdo. Still, the idea that particles are real little beads surfing invisible waves is satisfying in a way Copenhagen never was. And it's a good reminder that even in physics, there's more than one way to tell the same story. But just when you think we're done with interpretations, along comes a twist that throws causality itself under the quantum bus, where choices you make now can apparently rewrite what happened in the past. Delayed choice, changing the past from the present. By now, you probably know the double-slit experiment, the one where particles act like waves if you don't watch them, but like particles if you do. It's the gold standard for quantum mechanics makes no sense. Now imagine taking that experiment and adding a time travel plot twist. You decide after the particle has already passed the slits whether it should act like a wave or a particle, and somehow it obeys your decision retroactively. Welcome to delayed choice. This idea came from physicist John Archibald Wheeler in the 1970s. Wheeler had a mischievous way of asking what if, questions that drove other scientists to either laugh or cry. Here's the setup. Start with the standard double-slit experiment. Fire a single photon or electron toward the slits. If you let it travel undisturbed, it behaves like a wave, going through both slits and creating an interference pattern. If you put detectors at the slits to find out which one it went through, the wave pattern disappears. It acts like a particle. No mystery there. Well, no new mystery. The usual quantum one still applies. Now Wheeler's twist. Wait until after the photon has passed the slits, when it should have already decided whether it's behaving like a wave or a particle, and only then decide whether to measure which path it took. In other words, make your measurement choice too late to influence the particle in any normal cause and effect way. What happens? The photon still plays along with your late decision. If you choose to check which slit after the fact, the interference pattern disappears, as if it had gone through only one slit all along. If you choose not to check, you get the interference pattern, as if it had gone through both. It's like sending a student into a school building with two doors, and only after they're already inside deciding whether they should have used just one door or both, and then the past rearranges itself to match your choice. The obvious question: does this mean we're literally changing the past? That's what it feels like. But most physicists would say no. Instead, they'd tell you that in quantum mechanics, the past isn't fully determined until the present measurement locks it in. Until then, it's not that the particle already did something and we're changing it. It's that it existed in a superposition of possibilities, and your measurement picks which version becomes the official history. Wheeler even took this further with a cosmic delayed choice thought experiment. Imagine a distant galaxy billions of light years away, with a massive gravitational lens, a giant object that bends light between it and Earth. A single photon from that galaxy could take two paths around the lens before reaching our telescope. Billions of years later, today, we decide whether to set up our experiment to detect which path it took, or to let the paths interfere like a wave. And the photon, which has been traveling since before humans existed, will still behave according to our choice now. It's the ultimate late edit to the universe's story. Whether you interpret this as the present shaping the past, or the past being undefined until the present, depends on which quantum philosophy you like: Copenhagen, many worlds, pilot wave, or some other flavor. But whichever you pick, the message is clear. In quantum mechanics, reality doesn't lock in until it absolutely has to. And that brings us to perhaps the most unsettling question of all. If reality doesn't solidify until measured, what does that say about you and your ability to make choices? Because the next thing we have to talk about is whether quantum mechanics leaves any room for free will, or whether we're all just very sophisticated probability machines. Quantum and free will. Are we just probability machines? Free will. It's one of those topics that's been argued about for thousands of years, usually by philosophers with wine in one hand and a very smug expression. But in the age of quantum physics, the question gets a new, unsettling twist. Are we truly making choices, or are we just very complicated machines running on quantum randomness? First, a quick recap of the two old camps. Camp 1. Determinism. Every event is the inevitable result of what came before. If you knew the position and velocity of every particle in the universe, you could calculate the entire future, like reading a script. In that world, free will is just the illusion of making a choice. You are always going to do what you did. Camp 2. Indeterminism. The universe has room for genuine unpredictability, so maybe your choices aren't completely pre-written. Classical physics mostly lean deterministic. Quantum mechanics blows that up. At the subatomic level, outcomes aren't fixed, they're probabilities. A particle might have a 50% chance of being here, 50% there, and nothing can tell you exactly where it will end up until it's measured. Some people hear that and think, aha, randomness means freedom. Not so fast. Randomness isn't the same thing as free will. If your choice comes down to a quantum coin flip in your neurons, that's not you deciding. That's just physics rolling dice. Instead of a predetermined machine, you're now a machine with a random number generator inside. That's not exactly empowering. But here's where it gets interesting. Your brain is a staggeringly complex network of about 86 billion neurons, and each neuron communicates through electrical and chemical signals. Some scientists argue that certain processes in the brain, like the firing of neurons at the threshold of activation, could be influenced by quantum effects. If that's true, it might mean your thoughts, decisions, and even your sense of self have a tiny quantum component. This idea pops up most famously in the work of physicist Roger Penrose and anesthesiologist Stuart Hameroff, who proposed that quantum states inside microscopic structures in neurons, called microtubules, might contribute to consciousness. Their theory, orchestrated objective reduction, or OR, is controversial, and many neuroscientists think the brain is too warm and noisy for delicate quantum states to survive. But if they're right, it would mean the quantum world isn't just underlying your body, it's woven into your mind. Even if quantum physics plays a role in brain function, we're still left with the same puzzle. Does that role give you control, or just inject randomness into the mix? If free will exists, maybe it's not about escaping the laws of physics, but about how those laws allow complex systems like human brains to generate self-driven, goal-oriented behavior. And then there's the truly unsettling possibility. What if you are simply the emergent output of billions of probabilistic processes? Not a captain steering the ship, but the ship itself, with every turn determined by the combined forces of physics and chance. So where does that leave us? In one sense, quantum mechanics does open the door to a universe that isn't clockwork predictable. In another, it reminds us that unpredictability isn't the same thing as personal agency. Maybe the real takeaway is this: free will, whatever it is, isn't about defying physics. It's about living inside it, making decisions, taking actions, and telling yourself a story about why you chose them. Whether that story is fully true or not, well, that's between you and your neurons. And now, speaking of unsettling stories about reality, it's time to zoom all the way back out. Because quantum mechanics doesn't just shake up particles, brains, and lab experiments. It might also be the key to understanding why the universe itself is so bizarrely, improbably structured, and whether we're just one branch in an infinite cosmic network. The multiverse, from particles to cosmic branching. If quantum physics were a Netflix series, the Multiverse episode would be the one where the writers go, screw it, let's just make everything possible happen at once. And somehow, it's not even the weirdest thing in the season. We've already brushed against the multiverse in many worlds, where every quantum event creates a branch of reality. That's one kind of multiverse, a quantum one. But physics, being physics, couldn't just stop there. It's gone and invented several different kinds of multiverse theories, each stranger than the last. Let's start small, quantum multiverse. In this version, every time a particle has multiple possible outcomes, the universe splits, creating separate timelines. Infinite branches, infinite U's, infinite ways to embarrass yourself at a party. We covered this in many worlds, so we'll move on before you get vertigo. Next up, cosmological multiverse. This one comes from the theory of inflation, the idea that in the first fraction of a second after the Big Bang, the universe expanded faster than the speed of light. Inflation might not have stopped everywhere at once. Some regions kept expanding, forming, quote, bubble universes, each with its own space, time, and maybe even different physical laws. Our universe could just be one bubble in an endless cosmic foam. In another bubble, gravity could be stronger, atoms might be unstable, and life could look like something out of a nightmare fuel painting. Then there's the brain multiverse. Courtesy of string theory, picture our universe as a giant sheet, a brain, floating in a higher dimensional space. Other brains could be floating nearby, each one its own universe. If two brains collide, you might get a new Big Bang, which means our universe might just be the result of an interdimensional fender bender. And, because physics never runs out of wild ideas, there's also the mathematical multiverse. Proposed by cosmologist Max Tegmark, it says every mathematically possible universe exists, not just as equations, but as actual realities. Somewhere out there is a universe identical to ours, except you're wearing a different shirt. Somewhere else, the laws of physics make no sense at all and somehow still work. Now you might be thinking, okay, but how do we test this? And here's the awkward truth: we can't. At least, not yet. These other universes, if they exist, might be forever beyond our reach. That's why some scientists love the multiverse idea, while others call it philosophical window dressing dressed up in physics jargon. But here's the fun part. The multiverse isn't just abstract speculation. Certain versions could explain real mysteries, like why the constants of nature in our universe seem just right for life. In a multiverse with many different sets of physical laws, most universes would be lifeless. We just happen to live in one of the rare Goldilocks universes. Not too hot, not too cold, not too gravitationally crushing, because, well, we couldn't be here to ask the question otherwise. Of course, this explanation has its own snarky counterpoint. Maybe the universe is fine-tuned for life because life adapted to the universe, not the other way around. In other words, stop flattering yourself. In the end, the multiverse is one of those ideas that makes your brain buzz. It could be the ultimate cosmic truth, or just a fancy way of saying, we don't know why things are like this. Either way, it's fun to think about, because it stretches your mind past the comfortable boundaries of, everything is what I see in front of me. And speaking of boundaries, there's one place where quantum mechanics and the grand structure of the universe collide head-on, a frontier where even our best theories start to break down. It's the holy grail of modern physics, and it might be the only way to unify the smallest particles and the largest cosmic structures. The quest for quantum gravity, where physics finally breaks. Physics is supposed to be the one subject that has all the rules. We've got quantum mechanics for the small stuff, particles, atoms, molecules. We've got general relativity for the big stuff, stars, galaxies, the shape of the universe itself. Each one is beautiful in its own right. Each one has been tested to absurd precision. And each one works perfectly until you try to use them together. That's where the trouble starts. Quantum mechanics says the universe is a probabilistic sea of fields and particles. Relativity says space and time are a smooth fabric that bends and curves under mass and energy. Put them together in the same equation, like you'd need to do to understand black holes or the very beginning of the Big Bang. And the math doesn't just get ugly. It explodes into nonsense, infinities everywhere, as if the universe is just trolling us. This is why physicists are obsessed with finding quantum gravity, a single framework that merges the two. It's the holy grail of theoretical physics. It would tell us how gravity works on the tiniest scales, where space-time itself might not be smooth but foamy and jittery, like a quantum ocean. There are a few contenders, each with their own fan clubs. String theory says that particles aren't little points. They're tiny vibrating strings of energy. Different vibration patterns give you different particles, like guitar strings producing different notes. Gravity pops out naturally in this model, and it's mathematically elegant, but it also demands extra dimensions, up to 11 of them, which is great for sci-fi but not so easy to confirm in a lab. Loop quantum gravity goes in a different direction. It says space itself is quantized. Instead of being a smooth fabric, space-time is made of discrete chunks, loops woven together like an invisible 3D chainmail. In this view, you can't zoom in forever. Eventually you hit the pixels of space. There are also more exotic approaches, holographic principles, that suggest the entire universe might be like a 3D projection of information encoded on a 2D surface. As if reality is a cosmic VR headset and we're all just very committed avatars. Why does any of this matter? Because quantum gravity isn't just about bragging rights. It's about understanding the most extreme places in the universe. Inside black holes, relativity predicts a singularity, a point of infinite density, but quantum mechanics screams, "Nope," and refuses to play. At the Big Bang, the same problem appears. Relativity says infinite everything. Quantum mechanics says invalid input. Only a unified theory can tell us what really happens when the universe is pushed to its limits. And here's the frustrating part. We don't have experiments yet that can directly test these theories. Black holes are too far away to poke, and the energies needed to probe space-time at the quantum scale make the Large Hadron Collider look like a AA battery. For now, quantum gravity lives in the realm of thought experiments, mathematical models, and the occasional bold press release. But someday, maybe with new telescopes or gravitational wave detectors, we'll catch nature doing something so extreme it forces the answer into the open. And when that happens, we won't just have solved a physics problem, we'll have rewritten the very blueprint of reality, which makes this a fitting place to pause our journey. Because quantum physics isn't just about particles and equations. It's about a universe that constantly resists being fully understood. Every answer opens 3 more questions. Every experiment shows us something we weren't expecting. And maybe that's the real magic. Not the certainty, but the endless chase. All right, let's take a breath. We've just been through the heavy stuff. Wave-particle duality, uncertainty, entanglement, quantum fields, Higgs bosons, basically the full buffet of reality's deepest and weirdest rules. If your brain feels like it's been quantum entangled with a blender, congratulations, you've been paying attention. Up to now, we've mostly been talking about theories, the mathematical blueprints of how the quantum world works. But here's the thing. Physicists aren't just sitting in dark rooms scribbling equations on chalkboards. They're doing things with this knowledge. Dangerous-sounding, occasionally ridiculous, reality-breaking things. Because once you understand the rules, the next step is obvious. Try to break them. Or, at least, bend them until the universe looks at you like, wait, you can't do that. That's where we're headed now. These aren't your standard textbook experiments. We're talking about setups where particles refuse to move just because you're watching them, where you can detect a bomb without setting it off, where you can take a photograph using light that never even touched the subject. Stuff that sounds like it belongs in a sci-fi short story, except it's in peer-reviewed journals. So sit back, loosen your grip on what you think common sense means, and prepare to meet the quantum troublemakers, the experiments that shouldn't be possible, but are. The quantum Zeno effect, freezing change by watching. Here's a weird question. Can you stop something from happening just by checking on it often enough? Not by interfering physically, not by blocking it or freezing it, but simply by observing it so much that the universe gets awkward about moving forward. Sounds ridiculous, right? But welcome to the quantum Zeno effect, where reality starts behaving like a shy kid who forgets their line in a school play the second you look directly at them. Here's the gist. In quantum mechanics, a particle's state, where it is, how fast it's moving, what it's doing, is not a fixed thing until it's measured. Between measurements, it evolves, changes, shifts. But if you keep measuring it quickly enough, the act of measurement keeps forcing the system to reset back to the starting point. It's like hitting rewind every time the movie starts to play, so the plot never moves forward. Imagine a radioactive atom that's supposed to decay after some amount of time. If you watch it constantly, measuring whether it's decayed yet, quantum mechanics predicts and experiments confirm it decays slower. In extreme cases, you can almost freeze it entirely. The name comes from Zeno's paradox, the ancient Greek puzzle that says an arrow in flight is never really moving if you keep slicing time into smaller and smaller moments. Except now it's not philosophy, it's physics. The really strange part? This effect has been seen in the lab. Physicists have used cold atoms and superconducting qubits to show that rapid observation literally slows down quantum transitions. The more often you check in, the less progress the system makes toward its next state. This flips our normal thinking about time and change. In the everyday world, looking at something doesn't stop it from evolving. You can watch bread in the oven all day. It's still going to bake. But in the quantum world, too much attention can hold the bread in some pre-baked limbo. It's like the ultimate watched pot never boils. Except here, the pot really doesn't boil. And there's a twist. If you space out your observations differently, you can actually speed up the change instead. The so-called anti-Zeno effect. So by controlling when you look, you can either hold reality in place or push it forward faster than it would have gone. This isn't just a cute curiosity. It has real implications. In quantum computing, unwanted observation by the environment, what physicists call decoherence, can lock up quantum states or ruin computations. On the flip side, careful timing could be used to deliberately control quantum processes. So the next time someone tells you, "Just checking in," remember, in the quantum world, that phrase could literally stop time. And if you're thinking, wait, so the universe changes faster when I don't look? Yeah. Welcome to the kind of nonsense that makes physicists stare at the ceiling at 3 a.m. The Electrons bomb tester, detecting without touching. Here's the setup. You're in a room full of bombs, not movie prop bombs, real ones. And they're so sensitive that the smallest touch will set them off. Your job? Find out which ones are live and which ones are duds, without touching them. Sounds like the worst game show ever. In the normal world, this is impossible. If your test interacts with the bomb at all, you're risking a big kaboom. But in quantum mechanics? There's a loophole so bizarre it sounds like cheating. You can detect a live bomb without ever triggering it. This is the Electrons bomb tester, an experiment dreamed up in the 1990s by two Israeli physicists, Avshalom Elitzur and Lev Weidman. And no, they weren't building an actual bomb range. They were exploring one of the weirdest implications of quantum physics, interaction-free measurement. Here's the magic trick in simple terms. Imagine a particle, like a photon, that can take two paths through a setup. Call them path A and path B. If both paths are open, the photon's quantum wave nature makes it interfere with itself, producing a predictable "I went both ways" pattern at the detector. But if there's a bomb in path A that would absorb the photon, the interference pattern changes, even if the photon didn't actually go down path A. Translation: the photon knows the bomb is there without ever hitting it. It's like you somehow know your neighbor's home without ever knocking, calling, or seeing them, just because the possibility of meeting them changes how you act. In the lab, scientists don't use bombs. They use ultra-sensitive detectors or absorbers that act like them. The key is that quantum superposition allows the particle to explore all possible paths at once, and the act of blocking just one path changes the outcome in a measurable way. The mind-melting part? In some cases, you can confirm a bomb is live without any particle ever touching it. Zero interaction. Zero, boom! This isn't just a fun thought experiment. It's actually been demonstrated with photons, electrons, and even atoms. And it's not just about bombs. Interaction-free measurements have potential in delicate imaging, where shining light directly on something would destroy it, like studying fragile biological samples or quantum systems without disturbing them. Of course, the whole thing raises an uncomfortable philosophical question. If something can affect reality without ever interacting, how much of the world around you is shaping your life just by existing in the range of possibilities? And yes, the idea that we can detect bombs without touching them sounds like the start of a terrible spy movie, But in the quantum world, it's just Tuesday. The delayed choice quantum eraser, erasing the past. Here's a question that will make your coffee taste weird. Can something you do right now change what happened earlier? Not in the "I regret eating that burrito" way. I mean in a literal, physics-based time warp kind of way. That's the mind-bending territory of the delayed choice quantum eraser. This experiment sounds like something made up by a screenwriter who just discovered quantum mechanics, but it's been done in the lab, and it makes reality look negotiable. To understand it, we have to start with the double-slit experiment, the greatest mood swing in science. Fire particles, like photons, at a wall with two slits. If you don't watch which slit they go through, they act like waves, interfere with themselves, and make a striped pattern. But if you do check which slit each particle took, the interference vanishes, and you get two boring piles. Observation changes the outcome. That's already weird enough. Now the delayed choice twist. What if you wait to decide whether to observe the particle until after it's already gone through the slits, maybe even after it's hit the detector? John Wheeler, the physicist who proposed this in the 1970s, said the choice to measure could be delayed so long that it seemed to rewrite what the particle had done in the past. And here's where the eraser part comes in. Physicists set up an experiment where the which path information can be recorded but also erased later. If the information is erased after the particle has gone through the slits, the interference pattern comes back, as if the particle had never been measured. But if the information is kept, the interference vanishes. The wild part? This decision to erase or keep the data can be made after the particle has already been detected. It's as if the particle's earlier behavior, whether it acted like a wave or a particle, was determined retroactively. Now, does this mean time travel is real? Not exactly. You can't send a message to your past self or stop your teenage haircut mistakes. What it does mean is that in the quantum world, events don't have fixed histories until all the relevant information is settled. The past is, in a very real sense, still up for negotiation until the final measurement. Why does this matter? Besides giving you something to ruin family dinners with, it challenges our most basic assumptions about cause and effect. It's like the universe is saying, don't assume I've decided how this story goes until the last page is written. So next time you think the past is set in stone, remember, somewhere in a quantum lab, scientists are erasing it, and the universe is calmly rewriting itself as if nothing happened. Hardy's paradox, particles that meet without meeting. Let's play a game. Two people walk into the same room, except they don't. They interact, change each other's behavior, and then leave, all without ever actually being in the same place. Welcome to Hardy's paradox, one of those quantum experiments that makes you want to check if your coffee has been spiked. It's named after physicist Lucien Hardy, who in 1992 came up with a thought experiment that has since been tested in labs. And yes, the results are as ridiculous as they sound. Here's the easy version. We know from quantum mechanics that particles, like electrons or photons, can be in a superposition, essentially taking multiple paths at once, until measured. Hardy imagined a setup where you send an electron down one path and a positron, its antimatter twin, down another. The paths are arranged so that in some cases, both particles could end up in the same region and annihilate each other. Total mutual destruction. Now here's the trick. Sometimes the detectors show that both particles acted as if they met and avoided annihilation, even though, according to classical logic, they never actually occupied the same space at the same time. It's like two drivers slamming on the brakes at an intersection to avoid a collision, except traffic cameras later prove they were never in the intersection together in the first place. So what's going on? The only explanation that fits the math is that quantum superpositions allow the possibility of them meeting to influence the outcome, even if, in the final real history, the meeting never happened. The shadow of what could have occurred changes what does occur. In the lab, this is done with photons and interferometers, devices that split and recombine light beams. Measurements reveal patterns that can only be explained if the particles somehow knew about each other's presence without direct interaction. Why does this matter? Because it's another nail in the coffin for the idea of a fixed, local reality. The comforting picture where events happen in a neat chain only caused by what's directly in contact. Hardy's paradox says nope, possibilities themselves can have consequences, and non-events can still leave fingerprints on reality. In other words, in the quantum world, almost counts. Almost meeting, almost interacting, almost colliding. All of these nearlies can still alter the outcome, which is kind of like finding out your life is shaped just as much by the things that didn't happen as by the things that did. Bose-Einstein condensates when thousands of atoms act as one. Most of the time, atoms are like people at a crowded concert, bumping into each other, jostling for space, each doing their own thing. Even if they're part of the same material, they act individually. But in 1995, physicists figured out how to take thousands, even millions of atoms, and get them to behave as if they were a single, unified superatom. This is the Bose-Einstein condensate, BEC. A state of matter so strange it was first predicted in the 1920s by Albert Einstein and Indian physicist Satyendra Nath Bose, but no one could make it for 70 years. Why? Because to create it, you have to take atoms down to just a few billionths of a degree above absolute zero, the coldest possible temperature in the universe. That's colder than space itself. Here's why it's weird. At normal temperatures, each atom's quantum wave is so tiny you can't notice it, like people dancing out of sync in a club. But when you cool atoms down near absolute zero, their individual quantum waves stretch out until they start overlapping. And when they overlap enough, the atoms lose their individuality and merge into one giant quantum state. Imagine thousands of dancers suddenly moving in perfect synchronization, not because they're watching each other, but because they've literally become part of the same dance. Measure one atom's state, and you instantly know the state of all of them, because they're all the same wave. In the lab, scientists make BECs using lasers and magnetic traps. First, they slow the atoms down with carefully tuned laser beams. Yes, you can slow atoms with light. Then they use magnetic fields to hold and cool them further, until boom, well, not boom, more like shh, you get a ghostly droplet of matter that behaves like one giant, delicate particle. What's it good for? Besides being a Nobel Prize magnet, BECs are giving us a test bed to explore quantum mechanics on a scale big enough to see under a microscope. They're used to simulate black holes, study superfluidity, where a fluid flows without friction, and even test theories of quantum gravity. And here's the eerie part. When you look at a Bose-Einstein condensate, you're not looking at a bunch of atoms anymore. You're looking at a single wave of matter spread out across thousands of particles. It's as if individuality itself has been erased, replaced by pure, collective identity. In other words, the Bose-Einstein condensate is the closest thing physics has to a perfectly in-sync flash mob, except the dancers are frozen to within a billionth of a degree, and the choreography is written by the universe itself. Quantum ghost imaging, taking pictures with light that never touched the object. Imagine you walk into an art gallery, point a camera at a painting, and somehow capture a perfect photo without any light from your camera ever hitting the painting. No, this is not invisibility cloak stuff or spy gadget nonsense. It's real, and it's called quantum ghost imaging. It sounds like cheating because it is, but in the best quantum way. Here's how it works. You start with a light source that spits out pairs of photons that are entangled, meaning they're connected in such a way that messing with one instantly tells you something about the other, no matter how far apart they are. Think of them as cosmic twins with a shared Google Doc. Now you send one photon from each pair toward the object you want to photograph, say a coin. But you don't actually detect that photon's image directly. All it does is bounce off the coin and land in a boring single pixel detector, the scientific equivalent of, yep, something's there. The other photon from each pair doesn't go anywhere near the coin. Instead, it flies off to a high-resolution camera. This photon has never seen the coin, but because it's entangled with the photon that did, the pattern of coincidences between the two detections reveals the image of the coin. In other words, the camera records the picture from a photon that never touched the object. The image comes entirely from the spooky correlations in the entangled photon pairs. It's a bit like asking a friend to attend a concert, having them call you while you sit at home, and somehow, from just their breathing patterns, reconstructing the entire set list and stage layout. Sounds impossible, but quantum mechanics doesn't care what you think sounds impossible. Why is this useful? Because sometimes shining light directly on an object is a bad idea. Maybe it's too fragile, too light-sensitive, or in a dangerous environment. Ghost imaging lets you use harmless, low-energy light on the object, even infrared or ultraviolet, while collecting the image with a totally different kind of light that never went near it. In the real world, scientists have used it to see through scattering media, peer around corners, and even image biological samples that would be damaged by normal lighting. And the name ghost imaging? It's not just for drama. It's because the image comes from a ghostly partner photon that never interacted with the thing you're looking at. You're literally photographing the idea of the object, as whispered through quantum entanglement. So the next time someone tells you, "Pics or it didn't happen," you can tell them, "Fine, but my camera never went near it, and it still counts." The Aharonov-Bohm effect, changing particles with fields that don't touch them. Here's a trick question. If something doesn't touch you, can it still affect you? In everyday life, the answer is obvious. No. If I wave my hand near your coffee cup, it doesn't change the taste of your coffee unless you have trust issues. But in the quantum world, oh, absolutely. Enter the Aharonov-Bohm effect, where particles get influenced by something that never actually touches them. Here's the setup. You take a beam of electrons, tiny charged particles, and split it into two paths so they go around opposite sides of a cylinder. Inside that cylinder is a magnetic field. Here's the catch. The magnetic field is completely contained. The electrons never go through it. In fact, the region where the electrons travel has exactly zero magnetic field. Classical physics says, well, nothing's there, so nothing changes. They should behave as if the field isn't there at all. Quantum physics says, hold my beer. Even though the electrons never touch the magnetic field, their phase, the part of their wave function that determines how they interfere when they meet again, changes depending on the strength of the enclosed field. When the two paths recombine, the interference pattern shifts, as if the electrons somehow knew about the magnetic field hiding in the middle. The explanation? In quantum mechanics, it's not just electric and magnetic fields that matter. It's the potentials that generate them. These potentials exist everywhere. Even in places where the field itself is zero, the electrons are sensitive to that invisible backdrop, and it alters their wave behavior without direct contact. In plain English, it's like you walk down two identical hallways, neither of which has any obstacles, but when you meet your friend at the other end, you've somehow ended up out of step, just because there was a locked room between the hallways containing something you never saw. Why should you care? Because it means empty space isn't truly empty. Even in areas with no measurable force acting on a particle, the underlying quantum landscape can quietly change how that particle behaves. It's proof that the universe isn't just about what's there. It's also about what's around there. This effect has been tested and confirmed in the lab, and it's more than a curiosity. It shows up in superconducting circuits, quantum electronics, and even in the design of certain nanoscale devices. And philosophically, it's unsettling. It says you can be influenced by things that never touch you, never interact with you in any traditional sense, but still change your outcome. In other words, quantum physics just invented long-distance manipulation. Somehow I'm not surprised.